Questo.
Okay, so thank you very much everyone for attending. Today we have the honor to have here seminar by Iurii Sushch. He did his bachelor and his master in Ukraine. Then he moved to do the PhD in Humboldt in Germany. And after that, he did several postdoctoral stays in places like South Africa, also in Desi, in southern Germany, and other very known institutes as LHAASO in Italy. Now, from last year, he is now a Cesar Nombera Fellow at CIEMAT, from where he is visiting, and he will be talking about PeVatrons. So let's listen what he has to tell us.
Thank you, Maria. Thank you very much for inviting me, for having me, for the beautiful weather, for some excitement was the destruction of the building. This is the great part. Yeah, I will be talking about PeVatrons and where to find them and what are they and do we know what they are. Why this here? So I will start from this plot of the was the cosmic ray spectrum, and basically what I want to talk about, like this cosmic ray spectrum here is that we believe that up to the knee in the spectrum at around 3 PeV, all these cosmic rays are of the galactic origin, so they're produced in the galaxy, and then above the ankle everything is of extragalactic origin. And then in the middle, it's not really clear. It should be some combination. It's not really clear where the galactic cosmic rays should end and where extragalactic should kick in. But I mean, there are some arguments that cosmic rays in the galaxy should be accelerated, not just to few PeV, but like at least to 10 or even 100 PeV to have a smooth transition here between galactic and extragalactic cosmic rays. But basically what we need is to find sources in the galaxy that will accelerate particles, protons to at least PeV energies, and that is apparently a problem. So the long-standing paradigm says that supernova remnants are the sources of galactic cosmic rays, and the main argument for that is that supernova remnants basically have enough energy to explain cosmic rays energy density at the low energies. And we do know that that particles are accelerated in supernova remnants at the shock. But whether they are accelerated to enough energies, it's not really clear. But it would also be nice to have the same type of sources, ensuring smooth spectrum up to the knee. So basically, the idea here is if you had like supernova remnants here, cutting at some energy, and then something else introduced at higher energies. Basically, you would need some fine tuning in order to have the correct normalization here in place. And in order not to have it, people want us to have the one type of sources all the way to the. And so recently there were some results from DAMPE showing actually that the cosmic ray spectrum is not really that smooth as we thought. So basically, these new measurements here, which are going almost to PeV energies, basically show that you have a softening of the spectrum at GeV energies, at TeV energies, and then above 100 TeV you have a hardening again. And this could actually be an indication of another component coming in place here. So basically, of something like this. But yeah, I will start here from still from the supernova element paradigm and the question whether they can accelerate protons to PeV energies. We don't really see this in observation. So what we see in gamma rays that are basically the messengers of high energy protons or electrons. We see the cutoffs on everywhere. So here you see a sample of different supernova remnants of different ages, where you have young supernova remnants below 1,000 years, which are believed to be hadronic, and was a flat spectrum here, and then the cutoff at around TeV. Then you have middle-aged supernova remnants that have a cutoff at high energies, but they are mostly leptonic remnants. And then you have older remnants with the soft spectrum here, and again they basically you don't see anything if you go to higher energies. So this is in fact just a side note. This is actually this behavior is kind of what you expect in simulations. So here what you see in the plots here, and don't look at the halo, no halo, whatever. Basically what I want to see here is that and also don't look at the normalization, because there is something that is parameter dependent. But what I want to show here is that you have the gamma ray spectrum from hadrons at young stages of evolution, and the spectrum is flat. Then you have at higher ages the leptonic spectrum, and then at for all the remnants you have the soft spectrum of gamma rays. And this is this is coming from numeric simulations of particle acceleration and transporting supernova remnants for like thousands of years throughout the whole evolution of the remnant. But anyway, so at most the gamma ray spectrum that we observe reaches 10 TeV. So they have the cutoff at 10 TeV that would correspond to 100 TeV in the maximum energy of protons. So something way below what we want. There was some promising news from LHAASO, where they detected this source up to tens of TeV, and basically it was overlapping. It was coincident with a supernova remnant. So yeah, could be the first supernova remnant PeVatron. And they showed that basically to explain the spectrum they need PeV energies. But the problem here is that it's coincident with supernova remnant, but there is also a pulsar nebula there, and the morphology that you see here, the energy dependent morphology, how the shape of the source is changing as you go to different energy range, is basically not something you would expect from a supernova remnant. So most probably this is not supernova remnant and not hadronic emission. Then another point is that so LHAASO started detecting a lot of PeV sources, but most of those sources are in fact coincident with pulsars, with energetic pulsars, and can be explained by those pulsars within an atomic scenario. And if you want to ask questions about this, you have Emma and Ruben here who can answer about those questions. Yeah, so these are the exceptions. This is one the exception that I will talk more here about, is the Cygnus OB2, where you have a star cluster and you also have a microquasar. So what are the alternatives to supernova remnants? This is exactly the PeVatron that I was showing as an exception here. and you have a power law spectrum detected up to 2 PeV. So basically, you do have a PeVatron there, but it's not really clear what is the source there in the Cygnus region. So you have there is a binary system with a pulsar, there is a young stellar cluster, and there is a microquasar. And the last two became quite popular recently, also because LHAASO detected 5 out of 12 microquasars in 2024. And some of them were previously detected by Heston and Hope. And the special case here is SS43, where you kind of see that the new component is emerging if you go above 100 TeV. So basically, at 1 to 25 TeV, you have a source which shows like a two-jet structure, and it's nicely aligned with what Hess sees. Here you have assigned contours. So basically, you have the two-jet structure, and those jets are believed to be of atomic origin. While here, if you go to 25 to 100 TeV, you start seeing the different component emerging. And if you go above 100 TeV, you see a completely different morphology here. You don't see jets anymore, but you see a blob here, which is also coincident with the molecular cloud here. So basically, if you say that this is hadronic, this is of hadronic origin, this guy's also claimed that if you have like 10 sources like that, that would explain the problem flux at 1 PeV. So basically, that would explain the energy density in the cosmic ray spectrum. There are quite some questions to that and to the assumptions that they make, but I will maybe come back to this a bit later. I have it written here, so maybe I can also say it already now. Yeah, so basically they claim that that you can yeah, so this is the hadronic component, and so basically the assumption that they do in order to explain the cosmic rays at 1 PeV is they assume a quite hard spectrum, and with that having a very low so so they have quite high overall luminosity in protons, and it's not really clear whether you can even get for this source. So there are other sources. This is V4641 Sagittarius, which has even more convincing spectrum, where the spectrum goes all the way up to PeV with a very high flux. So yeah, so it is, pretty strong evidence that microquasars should contribute to cosmic rays at around me. So they should be strong contributors at PeV energies, but in order to have them like completely taken over and completely taking care of that energy range in the cosmic ray spectrum, some fine-tuning will be needed. I mean, we will need to have enough sources, enough luminosity in those sources. This work was done already by some people, and this is the paper from 2025. So basically, you have here you have the cosmic ray spectrum, and here you have the contribution. So in cyan you have the contribution of so-called typical sources, so meaning supernova remnants, and then here you have the contribution of microquasars. The difference between those two plots is that here they plot only historic microquasars, so not taking into account microquasars that are active today. So like only those that were in the past and that contributed to the cosmic ray C. And here they include everything, so also all the microquasars that are active today. And basically you can see already here that you need all the current microquasars in order to explain this. But also you this normalization that you have there is basically it's quite purely constrained. So there are lots of free parameters here with which you can play, and and get and depending on that you either fit the data points or not. But the main problem here, I would say, is that you absolutely need the current sources, and that basically makes a problem for the isotropy of cosmic rays, because depending on where those sources are and where you are, it changes the cosmic ray density, and basically it will also it's not really clear, at least to me, maybe for these guys it is, how the cosmic rays will be effectively isotropized, that we still see them isotropically coming from all directions. Just a fun fact, both the papers, the LHAASO paper on microquasars and this paper, are still only on archives, so they are not accepted to any journals, so just mentioning that. This paper was appeared only in 2025, so I guess it's still in the review process, but the LHAASO paper appeared in 2024, and I guess it went to Nature first. They rejected. I don't know what's happening, but neither of these papers is accepted yet. Another alternative sources are young massive stellar clusters. And here I'm showing you the Westerlund 1, which is the most massive cluster in the galaxy. And you have a gamma ray emission detected by HAAS up to 100 TeV. And then you also have a shell-like structure that kind of agrees with the location of the termination shock, where you would expect that termination shock. So that gave rise to the idea that this is probably electrons that are accelerated at the termination shock. But both hadronic and electronic scenarios are feasible. It's not really clear yet how and where particles are accelerated. So what is special is about young massive stellar clusters, and especially compact stellar clusters, is that basically you have, if you have like all the stars compact here, you have dense collective wind from the stars, which forms a termination shock. And then you have a turbulent and amplified magnetic field in this wind from this collective wind from the stars. And then you have several sites of where particles can be accelerated. They can be accelerated inside the core at colliding shocks from different stars, or like from multiple shock reacceleration, or also in stochastic acceleration. They can be accelerated at the termination shock here, and they can also be accelerated by the supernova remnant shock, because all these stars are massive stars that eventually explode as a supernova. So if you have one star eventually exploding in the star cluster, and it expands in this medium which is dense and which has turbulent and amplified magnetic field, so you have good conditions for particle acceleration. So there was a lot of studies in the recent couple of recent years, like what are the acceleration should be most effective. So these are the 3D hydrodynamic simulations by Bio and collaborators in 2024, and what they claim that I mean, what they say is that what they see in their simulations is that basically the acceleration in the core is not effective enough and doesn't get us to the highest energies to PV energies. Then Molino et al. They looked at the particle acceleration at the termination shock. And in principle, what they show is that PV energy, so here you have PV here, and they looked at different shapes of the diffusion coefficient. And basically, they show that you can get to PV energies, but you can get to it only if you assume bomb diffusion. And if you to have bomb diffusion, you basically need to self-generate turbulence by cosmic rays, because if you have pre-generated turbulent magnetic field, this it will follow a Krykal-Kolmogorov cascade, and basically your diffusion will be Krykal-like or Kolmogorov-like. If you have that, then you will not really, also in their models, you will not really get to PV energies. So they do get PV energies, but only in very optimistic scenarios, and it's not really clear whether those scenarios are feasible. So they did also look into studying Cygnus OB2 with the model, and they do fit the emission with particles accelerated at the termination shock, but they also at the same time require quite high density inside the bubble, which is not really clear how you get those high densities. By high densities, I mean that they need like 5-10 centimeters particles per cubic centimeter, which is basically the same as you have outside the bubble. And the last thing I want to add here, that particularly for Cygnus OB2, it's not even clear if the termination shock is there, because apparently stars in the cluster are not compact enough, and 3D hydrodynamic simulations show that basically with winds from all the star, you don't really form a collective wind that would form a termination shock. So it's not really, so particularly for this source, it's not really clear where particles are accelerating. So so the termination shock is question marks, and then we come to the last scenario here, and that basically brings us back to the supernova remnant paradigm. So basically, you still kind of need a supernova remnant shock to accelerate particles. And these guys also show that it could be that actually this is the case in Cygnus OB2, where you have 50. So there you might have supernova exploding 50,000 years ago, and that supernova would produce a power law proton spectrum up to 2 PeV energies, and that would nicely explain. So this is the component of the supernova that would nicely explain the highest energy spectrum in gamma rays. So there are a few problems with this model, but I will come to it later. So talking about supernova remnants, how supernova remnants can they even theoretically get to those energies? And technically, maybe yes. So basically, if you just apply a very simple Hillas criterion, which is basically a geometrical limit, which is basically telling you that the size of your acceleration site should be we cannot accelerate particles to higher energies and then their gyro radius should not be larger than the size of the acceleration sign. If their gyro radius is higher, that's it. I mean, they escape. They are not contained in the acceleration size, so you cannot accelerate to high energies. And basically, just using this idea, you can get to PeV energies, but you need quite high magnetic field of hundreds of microgauss. So you need the interstellar medium magnetic field of 1 microgauss to be effectively amplified. This is actually what we see in a couple of remnants. We see the thin X-ray filaments here, which are basically from the width of those filaments is basically a measurement of your magnetic field, because they're explained by the cooling of electrons through synchrotron radiation. And that gives you numbers of couple of hundreds of microgauss. So basically, you see this happening in supernova remnants. And the way it is happening, so the idea is that the cosmic rays that are accelerated at the shock, they self-generate the magnetic turbulence, and they can do it through resonant instability or non-resonant streaming instability. And basically, the good part of the resonant streaming instability is that you have particles, you have cosmic rays generating turbulence at the scale that is needed. So with the K equal to 1 over gyro radius, so basically you will generate turbulence that will scatter the particles of the right energies. This you don't have in the non-resonant streaming instability, because perturbations grow initially on scales which are much smaller than the gyro radius of the particle. So basically, you need to somehow get to the right scales to be able to keep particles at the shock. But on the other hand, this instability separates at turbulent magnetic field, which is much larger than the initial background field, while this resonant instability separates at magnetic field, which is at the level of the background field. So in this case, you can get to much, you can amplify magnetic field much stronger. Another thing is that it also requires, the non-resonant streaming instability requires a quite low background field to be even excited, because basically you need to have the pressure of cosmic rays larger than the magnetic pressure in order for it to be excited. Yeah, so again, there was a lot of studies recently, a lot of simulations run by different groups, and basically the general idea that everyone kind of agrees is that you need to have special conditions to get to PeV energies. You need to have very high shock velocities. You need to have high density, and you need to have also the high magnetic field, but also you need to have an environment where your magnetic field at the beginning is low enough so you actually excite non-resonant streaming instability. And basically what was shown by, for example, Christopher and Blasi and Amato, and what was shown, I will show you now in our simulations, is basically you reach this only in some special cases. So what these guys were showing is that you reach PeV energies only if you have remnants that are more energetic than typical supernova remnants. So this is for the for supernova with the explosion energy of 10 to 52 Hertz. So we are working on particle acceleration in supernova remnants for many years already, and this is the code that we are using, and this is the I will not go into details of the code. I will just basically tell you what it does. So it basically consists of 3 blocks. It solves the transport for cosmic rays. It solves the hydrodynamic equations using Pluto, which is incorporated in the code, and then it solves transfer equation for magnetic turbulence. Or we can also just prescribe diffusion coefficient. So basically, we inject particles which are accelerated, and those particles generate turbulence, and then turbulence confines particles. So the whole thing is self-consistent, and this is solved in everything is solved simultaneously in 1D and time dependent. As an output, we get a spectrum of cosmic rays as a function of location and time, and then from that we can calculate all the non-thermal emission that we want, and also so we are working on incorporating neutrinos and stuff to calculate also neutrino fluxes. So in terms of the maximum energy, we were looking at the very young core collapse supernova remnants, and we were basically looking into the most optimistic scenarios. So here you have the parameters for the progenitor star, so for the wind of the progenitor star, and then we would expand the remnant into the wind of those stars. And as I said, I mean, those parameters are kind of on the high end of the parameter space, because we want to see like how far we can get at most. And then basically we simulate this for 20 years, and basically what we see is that we saturate at some maximum energy, and in the best case scenario we get to 600 TeV. And this is basically limited by the available time to growth turbulence before it cascades down. And basically at the beginning you also need some time to even start having enough turbulence there. So it saturates below 1 PeV. And this is these are the luminosity for those cases. The camera luminosities and the Fermi and the GeV, so the TeV luminosities and the GeV luminosities. But I will not stop that much here. I just wanted to say that it would be hard to test this and to detect them, because basically they peak where the gamma absorption by the photosphere of the star is the strongest. So this here you have the absorbed flux. Well, here is the unabsorbed flux, and basically, yeah, you just absorb most of it. So can we do better? Can we try to think of something to do better? And we actually can. And something which is not like really something super special. This is something that you observe, that you see in stars. And basically the idea there is that you have, before the explosion, different types of stars have this different kind of eruptions. And basically that forms shells around the star of the enhanced density. And you can have different nature of this kind of shells. So like for For LBV stars, you basically have episodes of higher mass loss. For red supergiant, you have this photoionized shells, but this is something that you observe actually, and that is there. And the question is, how would the whole thing change if you have a supernova going into this medium? So this is the density profile, and interacting with the sudden jump of density. So having a shell here, and so we modeled that, and basically with that, depending where we put the shell, we can get to over PeV, to even in some cases to 10 PeVs. And the basic idea behind this is that as the shock interacts with the shell, it slows down, while the particles that are already accelerated, they reside in the upstream of the shock, and they basically generate turbulence farther upstream. And once the shock passes this shell, it accelerates again, and it goes through all this pre-generated turbulence, and that basically increases the maximum energy that can be reached in those scenarios. And this will also enhance the gamma ray luminosities, and it will enhance gamma ray luminosities in the places where you interact with the shell or after the shell interaction. So not in places that are so in the moments of time where your gamma absorption may be not important that much. So basically, it would be interesting to see and to search for this kind of rebrightening in supernova some times after explosion, like half a year or a year or whatever, a couple of months. And this is something that we are working on now. We are trying to build a strategy of how to observe, how to detect this kind of rebrightings in supernova using different wavelengths. But the point here is still that those events are rare, and I mean, you really need to have specific conditions to get to PeV energies. So in order to explain to the cosmic ray spectrum, to the knee, you will need to have like all the supernova remnants giving you that, and then you don't really have it. So coming to the last part, basically checking this idea of a supernova exploding in the superbubble in the compact stellar cluster, and this is not something which is special, because majority of supernova do reside in stellar clusters. So what is special again? It's the dense collective wind, and it's pre-existing turbulence generating with wind collisions. And actually, simulations show that you can get up to 100 microgauss of pre-generated turbulence, like close to the core, and then you get up to down to like 10 microgauss at the termination shock. And maybe it's good enough to get to PeV energies. So basically, we just simulated that, and this is the profiles in which we simulate the supernova. So basically, this is density, velocity, pressure, temperature, and magnetic field. And for magnetic field, we take like 200 microgauss at the core, and then it corresponds to around 10 at the termination shock, and then it's compressed at the termination shock. So basically, this agrees well with what you would expect for like 100 typical Wolf-Rayet stars, and then you you take like 10% of their collective wind luminosity into the magnetic field. But I gotta tell you that this is a lot. This is more than what we have in Western One, which is the most massive cluster in the galaxy. And then we propagate the supernova remnant. So basically, this is the evolution of the supernova remnant. This is the shock radius, the shock velocity, and the shock compression ratio for two cases. For the classic case of 10 to 51 ergs, the explosion energy, and then the energetic was 10 to 52 ergs. And you see this first jump here for the velocity is where it interacts with the termination shock, and this second jump here, this is actually when you have because when you interact with the termination shock, you create the reflected shock that goes inside the remnant, hits the contact discontinuity inside, and goes back to the forward shock. And this is the moment when they interact again. So basically, you get a bit of a boost of the forward shock after some time. But the point here that I want to make is that basically when you, after interaction with the termination shock, you move into a very hot medium and your shock compression ratio becomes very small. So basically for the classic case, that basically switches off your acceleration because your compression ratio goes down to 2.5. And for the energetic case, you propagate faster, so and your shock is stronger when you hit the termination shock, so it's better. But anyway, it goes down. So and then for the diffusion, we use two basically scenarios where we take only pre-generated turbulence, and then it would follow either Kolmogorov or Bragg cascade. And we prescribe diffusion coefficient, or we use self-generated turbulence, so then we have bomb diffusion. But in this case, we actually need to lower down the magnetic field a little bit, because if we don't, then we will not even excite non-resonant stability. So basically what we get here at the saturation level is actually below the pre-generated turbulence as we assumed for this case. So for this runs we use lower magnetic field, so the background field. And those are the simulations. So basically you see the spectra at different times. Green for bomb diffusion, and then red and blue for Kraichgau and Kolmogorov. And then you also see the downstream spectrum, the upstream spectrum, and the total spectrum. And well, I mean, the whole point here is that you don't really reach PeV energy. So the special conditions that you have in super bubbles of star clusters, that they don't really help much. You do if you have energetic explosion, but basically you do get it for individual for isolated supernova remnants as well. And again, these are rare events. So yeah, so you basically end up with the same conclusion that we need specific conditions and rare events. And now you would ask me now, how did these guys get to the PeV energies for Cygnus OB2? And I will tell you, they have the very energetic explosion, and they assume bomb diffusion. Yeah, so whether it's so first of all, it's optimistic, and also I'm not sure if it's well justified. But yeah, basically my results do not disagree with their results. It's just that they were quite optimistic about it. So there is another possibility, and I will end with this, that there is some people start talking about mirroring effect, which is in business for some time already, but it's yeah, people started talking more about it now. And you do see this also in MHD simulations, and basically the idea is that you don't really have so I mean your particles do not really get trapped by diffusion, so to say. They basically get mirrored between the edges, the eddies of the magnetic field. And with this you kind of get a similar situation to the bomb regime. So they are effectively trapped in the thing. And yeah, I mean, if you get something like that, and if you get something like that in the super bubbles of stellar clusters, then yeah, then if you would get if you would apply bomb diffusion for the pre-generated magnetic fields as we assumed here, you will get to be the energy. So maybe this is the cure for the whole thing. So yeah, answering the question, what are the fantastic PeVatrons and where to find them? Well, we don't really know for sure. And that's basically it. I just want to finish this reminding you to support Ukraine, but not only Ukraine. We have lots of stuff to support in the world now. Thank you.
Thank you very much, Iurii, for telling us all what we know about cosmic ray acceleration up to PeV energies, especially what we don't know. Okay, so questions for Iurii. Okay, maybe let me start. I wanted to ask about so this model in which you have the shock that you are moving a bit farther away in order to get
The shadow.
yes, sorry, the shadow. Have you over here? So have you made any prediction on how many supernova remnants you can have like this, and how many we will need to account for all the PeV cosmic rays that we see?
We didn't do these calculations. I mean, it's really hard to do these calculations because you don't really have enough information. I would say you know that you see also you see the shells in optical and stuff.
But if you go to the next slide,
Yeah.
So over here you see the maximum energy that you're able to attain. But
Yeah.
how many protons are you able to get up to this?
How many protons?
Yeah, I mean, what
Well,
is
yeah,
the
so it won't be enough anyway. So.
yeah? So that is my question. How many of these supernova remnants would you need in order to explain all the isotropic PeV?
More than we have. More than we have supernova remnants in Denmark. Yeah, because I mean, it's not the point is not really that those are also specific cases, but also that you get to these energies only during short times at the beginning, and that's it. I mean, you don't accelerate to these energies consistently over the evolution of the remnants.
Yeah.
So you don't get enough protons. I mean, in principle, it needs to get like 10% of the energy into this, but yeah, but this is not the case. So yeah, so it's like it's far from what we need. So we need something else anyway.
So this is not a final solution in case
No.
these objects are found to be like this.
It would be cool to detect some of this and to see if we can actually get to those energies. Yeah. But it's also going to be quite difficult to detect them because you kind of have gamma ray emission coming the fastest. So like you cannot use the triggers from other instruments that much. So you can have maybe some triggers from radio because they're coming roughly in the same time, but like you cannot get, for example, triggers from optical because that emission is coming later on. So yeah, so it's going to be difficult, but if we detect them, yeah, that would be cool to see that we can get to PV energies, but still it will not be enough to explain what you will come.
All right, thanks. More questions?
Maybe I have one.
Sorry, go ahead.
Yeah, Paola, Mariana, Gonzalo.
More of a comment because it might interest you. I think the last paper is now published, but in some Chinese journal in December.
Ah, yeah, right. I saw it. It was published, and the results were changed, right?
Yeah, it was very much changed.
Yeah,
Chinese side.
yeah. The results were changed. Well, I mean, I'm still citing the results that I like more. I guess
Okay, Paola.
So, Iurii, I was wondering about, so you were talking about the absorption of the gamma rays. And I was thinking if you would have any clues about this emission, thinking about the secondary product that is like the pair of electrons that they will produce, you can somehow trace them in another wavelength, for example.
well, they should be. Yeah, I mean, whatever is yeah, whatever. Yeah, it's I don't show spectrum here. Yeah, I don't know spectrum. So, yeah, I mean, if you absorb TV gamma rays, then I mean, you would be able to see them through cascades. This emission you will be able to see in GV or so, but I think the excess will not be that large to make a difference there. And so basically you can see here that that also the GV, I think here we assume yeah. So from 1 to 300 GV, the Fermi flux. And the Fermi flux is also absorbed a little bit. So basically, huh?
You're talking about inverse Compton, for example, on these electrons in the GV band.
So I mean, this is just hadronic image, but yeah, but I mean, like if you absorb, if you will have gamma absorption, and then you will have electromagnetic cascades, and that will produce again emission, inverse Compton emission through at GV energies. That's true, but I mean the absorption here, I think the maximum absorption here is around 300 GV or so. So basically, and then it should re-emit I think below 1 GV the maximum would be. So there is nothing really with what you can observe this that much. And I think the excess will not be strong enough to really see it. We didn't calculate that, but yeah, but my feeling says that no.
Good.
I had a bit more technical main question about the bomb diffusion, because in principle you say that you need cosmic rays, no? But there is, in terms of bomb diffusion means that you have a flat turbulent spectrum, so you can have even a kind of flattish turbulent spectrum without cosmic rays. That you have to inject turbulence at different length scale, which on a so complex structure as a super bubble, it could happen, no? You have injection in the core plus large scale fluctuation in the bubble on the bubble size.
What would create the turbulence at all the scales?
Well, instabilities on the forward shock, which are
I
large.
mean, the idea here is that you basically create turbulence with winds at some coherent length, which is like kind of the size of the stellar cluster or whatever. And then it cascades down.
What I think is that you can have different length scale, or these different coherent length scale, like the instabilities at the
Sure, I mean, if you tell me how to do it, how to
No,
create that,
actually, it's something that, I mean, the point is that I think that it has never been investigated. Nobody have ever done like a full hydrodynamical simulation with the entire with the entire super bubble and stuff that. It would be interesting to see that, but a priori, I wouldn't exclude it.
I guess we don't know it. And I mean, I say, like, if you have bomb diffusion there, if you manage to get bomb diffusion in this pre-generated magnetic field, so pre-amplified magnetic field, you will get to PeV energies, yes. But
So maybe that is a point that it would be worth to investigate.
I guess the point is that it is an extreme case, right? A very extreme.
Well, maybe it is something that you can get it if you do an extreme fine tuning, or maybe something that it arises naturally. I mean, I don't know. That is the thing that.
But this is the thing. I mean, it's just that all this, you know, there are MHD simulations which show this mirroring effect, which basically mimics the bomb diffusion, and in terms of, confining particles. But all this is done at, I think, much smaller scale, so it's not really clear of how it's going to work at a larger scale. And but I mean, it is a possibility. Maybe they're much better confined than you think.
We always assuming, maybe we are mistaken in our premises. I mean, we always assuming the cosmic rays distribution is isotropic, but now we don't know the cosmic ray distribution, PeV energies or multi-TeV or hundreds of TeV. Now with the latest result from LHAASO seems that it's not that uniform. So that would solve somehow some of the problems we have.
If it agrees with the distribution of microquasars or not, then yeah.
I mean, one thing is the anisotropy, right? That is measured by the whole LHAASO, IceQ, and so on. These energies, and this is something we need to reproduce, right? But we don't know if on the other side of the galaxy we measure exactly the same flux as here. And so, you know, I'm saying it's right, and it can be that it is not.
Yeah, but I mean, I don't think that it's easily reproduced. So, and then anisotropy there is not surely that big. I mean, if you're talking about you know, SS433 or the other V whatever taking care of most of the cosmic ray flux, then we would really see a huge anisotropy.
Yes.
And I'm not sure that's not surely what we did.
You didn't mention at all the Galactic Center as a possible.
I did. I did. Let me show you.
It was very small.
Okay. That's the time that I was making a photo.
It's
That's that.
Low effect.
Yeah. Not even the ugliest. Okay. Any other question? If not, we'll close it here. Thank you very much, Iurii, again.
thank you for having me.
And you go for tapas.
Yay.